Good afternoon, children. Today we are going to discuss about work done when there is a volume change. When there is a volume change means when there is an expansion, that's an increase in the volume. It can be a compression, that's a decrease in the volume. So to study about that, we take a cylinder, as usual a cylinder, and a piston. Here is a piston. So let this be the piston. Like this. Now inside this, here is gas. This is full of gas. And the gas be at a pressure P. This area of this piston is marked as A. Because of the pressure, there is a force exerted. Because pressure is force by area, which means force is pressure into area. So P into A is the force acting here on the piston by the gas. So as a result, what happens is this piston is free to move. This is a movable piston. So this piston will move and it may reach somewhere else. That is, it is displaced by an amount dx, a small distance it undergoes, that is dx displacement it gets. Now the work done in during this process, during the small process, the work done, how I can write is, this work done, we all know that it can be written as the product of force and the displacement, F into dx. Force is F, displacement is dx. Remember, this is a case in which the force and the displacement are in the same direction. Now this force we can write as pressure into area into dx. Into dx it is PA dx. Now this area into dx, you see this A into dx is nothing but area is this height, dx is this length. This is nothing but the volume, the small volume of this much part, which I can write as the dV, a small volume. ADX is nothing but a dV, the small volume here. So I can write the work done W as, this is a small work, so let I give it as dW here also, because it is a work done for movement of dx distance. Small work done it is, so I will write it as P dV. Suppose this is an expansion process and from V1 to a volume V2 this happens. Not just for a small displacement, actually for a greater expansion. If it is expanded from a volume V1 to V2, then the total work done is the total work done from V1 to V2 is calculated as adding all the small work done, that is dW. This is the process called integration, that is addition of small work done from V1 to V2. This process is called integration. So here if you do that process, we get integration, or this is known as integral. It's a letter or symbol showing this process, integral from initial volume to final volume, that is V1 to V2, dW, that is P dV. Actually here volume alone is changing, so we do not bother about pressure. P we can take outside. P integral V1 to V2 dV. Actually we are adding the small volumes here alone. Pressure keeping it constant, we are adding all the small volume. So what happens is, we get the total volume, that is P is already here. This process integral V1 to V2 dV, you do this, you get it as V from volume 1 to volume 2. That means its result will be like this. After doing this process, what you need to do is you replace this V as V2, put a negative sign, then write V as V1. So you get P into V2 minus V1. This is the work done during volume change, expansion or compression. Now the same thing, instead of equation, we can do in the PV diagram. From PV diagram also we can calculate the work done, and this work done will be equal to, suppose an expansion process happens from V1, maybe a gas in a cylinder at high pressure, maybe pressure is very high. During this expansion process, this is an expansion process, so the pressure decreases, volume increases, V increases, P decreases. It has a final stage. This is the initial stage where high pressure, low volume, lesser volume, but final stage, low pressure, more volume, P2, V2. Now, in order to find the work done in this case, what you need to do is shade the area coming under this graph like this. Shade the complete area coming under this graph and measure this area mathematically. This area will be equal to the work done during this process. So it will be equal to the work done during this process. So that's how we can find the work done while expansion or compression. So this work done depends only on the initial, as per this equation, the previous equation, this work done depends only on the initial volume and final volume. It does not depend on the intermediate stage. That means in between what was the volume and all, we do not want to know. The initial volume and final volume alone we want to know. Now we have a law. We already discussed one law, that was zeroth law about thermal equilibrium. Now we have the first law of thermodynamics, which gives a relation between heat energy and the work done and internal energy. To understand it very simple, I can give you one example. You take a container like here, a container in which a gas is taken. Here is a cylinder with a piston. This is a movable piston, a free piston. The walls are adiabatic. This is an adiabatic wall. This is also an adiabatic wall. Here is also an adiabatic wall. There is gas inside this. Suppose you give heat energy down. Here you give heat energy. That heat energy I write as Q, or small amount Q, delta Q. What happens is the molecules gain more energy, more heat energy. Their kinetic energy increases. So there is an increase in the internal energy, delta U. A small increase in internal energy happens. At the same time, this gas molecule, as they gain more energy, they try to come out of this cylinder. They push this piston upward. They do a small work done. A small work is done by the gas on the piston. That means the heat you have supplied, that is delta Q, is used for two purposes. One is for changing the internal energy and work on the surrounding, dW, sorry, or delta W, the work done. This is known as first law of thermodynamics. This is just an example, but the law is same, that is delta Q is equal to delta U plus delta W. That is, heat supply to a system is equal to increase in the internal energy and work done on the surrounding. In this, depending on the situation, you have to give proper sign conventions. That means the heat given, if you give as positive, increase in the internal energy, that is delta U positive. Work done by the gas on the surrounding is positive. So this positive case alone I have given here. Otherwise, depending on the situation, you have to assign proper signs. This rule can be expressed in one more way. We already know this work done delta W, just now we got it as P V2 minus V1, that is P difference in the volume, P delta V. So giving that, we can write delta Q is equal to delta U plus P delta V. This is also an expression for the first law of thermodynamics. Another topic which we need to discuss is about specific heat of a gas, especially an ideal gas or a perfect gas. In chemistry, you have studied about an ideal gas. An ideal gas is a gas in which the molecular attraction, the intermolecular forces are very negligible. All molecules are free. That kind of a gas is called an ideal gas. Now coming to our topic, that is specific heat of ideal capacity, ideal gas. Specific heat capacity of ideal gas. That's what our topic now. You already know what is specific heat capacity. It is the heat required to raise the temperature of a body by unity, means 1 degrees per unit mass. That was specific heat capacity. For gases, when it comes to gases, we use the term molar specific heat capacity, because the amount of substance will be expressed in number of moles. So heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. That is specific molar specific heat capacity. Now we all know that this specific heat capacity depends on the volume, the amount of the substance taken, and also it depends on the pressure of the system. Two things it depends. One is the volume of the system and the pressure of the system. So for that, we have two different uh, specific heat capacities. One is Cp, that is molar specific heat capacity at constant pressure. Another one is molar specific heat capacity at constant volume, Cv. And this C, we know this is represented as 1 by n delta Q by delta T. This was the expression for this C, whether it is Cp or Cv. At constant pressure or constant volume, whatever it is, 1 by n delta Q by delta T. Let's take for 1 mole, which means n is 1. C is 1 delta Q by delta T. So if it is Cp, what we write is delta Q by delta T at constant pressure. Like this we will express. We'll put a bracket and we'll write P in that. Similarly, Cv is delta Q by delta T. We'll put a bracket. Below that we write V. That means it's heat capacity at constant volume. Cp and Cv, two terms. Now we can find out the relation between this Cp and Cv. Just let's try the relation between Cp and Cv. Just look at this equation, delta Q by delta T is Cp at constant pressure. So now what we can do is we can just take from first law, delta Q is delta U plus P delta V. Delta Q by delta T we have to take. Delta Q by delta T. So here delta Q by delta T if you take, you get a delta U by delta T plus P delta V by delta T, delta Q by delta T, plus P delta V 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 by delta T, plus P del Now this delta Q by delta T, if I put a bracket and if I write this is at constant volume, this is nothing but my CV. This is my CV. This means CV means this is at constant volume, this is also at constant volume. But there's a problem here, is change in the volume, delta V is change in volume, and this is at constant volume, which means at constant volume there is no change in the volume. So this term is 0, which means Cp is equal to delta U by delta T. Sorry, Cv is equal to, not Cp, Cv is equal to delta U by delta T at constant volume. Volume is constant. Similarly, let's try for Cp also at constant pressure. Cp is, as per this equation, delta Q by delta T at constant pressure. We write it as pressure is equal to delta U by delta T at constant pressure P plus P delta V by delta T at constant pressure. So this is not term, not 0 term. P delta V by delta T is there. Let this equation be equation number 1. And one more term we have to take is, one more thing we have to consider, that is the ideal gas equation. Let's take the ideal gas equation. The ideal gas equation is PV is equal to nRT. As we already told, for 1 mole N is 1, so PV is equal to RT. This is what our equation is. PV is equal to RT. Now look at this term. This is at constant pressure. What is P delta V by delta T? That's what we have to take. Here, if you take the differentiation of this, we have a delta of PV is equal to delta of RT. This is the differentiation, our D itself. This is a D itself. But it can be represented as a delta also, differential. So this is in the format UV formula. P delta V plus V delta P is equal to R delta T, because R is gas constant, universal gas constant, you know that. So R is a constant. So we are taking about P delta V by delta T at constant pressure. So these all we have to consider at constant pressure. We have to think how much it will be at constant pressure. So one problem is, this is okay, P delta V, plus here is a change in the pressure at constant pressure. Change in pressure at constant pressure is 0. R delta T, again not representing it as P. So here P delta V is nothing but R delta T. This delta T I can take here. P delta V by delta T is nothing but R. Let this be equation number 3. I am giving this equation number 2. Okay. So if I put the two equations together, if I take together, equation 1, 2, 3 you take, all the 3. Equation 1 I have a CV equal to delta U by CV is equal to delta U by delta T at constant volume. Cp I got equation number 2, Cp is equal to delta U by delta T itself at constant pressure, plus this P delta V by delta T, I got it as R. I have this as R. So now let's take this Cp minus Cv. This is delta U by delta T at constant pressure plus R minus delta U by delta T at constant volume. So this Cp minus Cv is equal to R, we get. This and this cancel. So this is the relation between Cp and Cv for an ideal gas. So for an ideal gas, specific heat capacity, their relationship at constant pressure and volume, their relationship is Cp minus Cv is equal to R, where R is the universal gas constant. You know that value is 8.314.